Hey everyone, welcome back, and today let's solve Leetcode problem 916 titled Word Subsets. So we're given two string arrays, words 1 and words 2, and a string B is a subset of a string A if every letter in B occurs in A, including multiplicity, which really means including the corresponding frequencies of letters that occur in B and A. So for example, the string WRR, notice how it's very important to note that we have two R's and one W. That string would be a subset of the string warrior. However, it wouldn't be a subset of world. Let's kind of look into why that really is. Now, the unique characters that this string has are indeed W and R, if we don't really care about frequencies. And to be fair, both these strings do contain the letters or characters W and R. And so you may be thinking, well, then why is WRR only a subset of warrior and not world? Well, because the problem specifically states that for a string B to be a subset of string A, it has to not only occur in A, it also has to occur in A including the multiplicity. In this case, we want exactly one W and two R's, because that's the frequency of R, to be in a larger string, or a superstring you can say, for this string to be a substring of that. In this case, although both of these strings have W and R, this world does not actually have two R's. It only has one R. However, this warrior, it has not only one W, as we see in WRR, but it also has two R's, as we see in RR, right? Every single string or character in this string appears in warrior, including its multiplicity. Basically, we have the same frequency of R, and we have the same frequency of W, which are all the characters we have in this string WRR. That's why, since world doesn't have two R's, it's not a superstring or of WRR, but WRR is actually a subset of warrior. So a string A from words 1 is called universal if for every string B is what we're going to call it in this problem. In words 2, B is always going to be a subset of A, which really means any string is going to be universal from words 1 if all the strings in words 2 are actually subsets of that string. And we need to simply return an array of all of the universal strings in word 1 in the form of a list, which we can return in any order, right? So to better understand this problem and for some good context here, let's go ahead and look at the examples here. So in example 1, we have our input array of strings words 1 to be the following. And in this case, words 2 is really just going to be two words or subsets of, actually in this case, only length 1. Believe it or not, it's just going to be the string E and the character O. And in this case, all of the universal words in word 1, or all the universal strings in word 1, would be Facebook, Google, and Leetcode. And so that's why we output those three strings in this return list. But why is that the case? Well, that's because these are the only three words in our input string words 1 that actually are universal. Or in other words, that mean that both E and O are subsets of these three strings. As you can see, Apple is not a superset of E or O, because of course it doesn't contain an O, right? No, notice how E is actually a subset of Apple. However, O is not a subset of Apple because it isn't actually a character that occurs in Apple, and so that wouldn't be universal. And we can say the same thing about Amazon. Amazon does have an O, so O is a subset of Amazon, but it doesn't have an E. So E is not a subset of Amazon, making Amazon not a universal word. And so the only three strings in this input array of words 1 that are universal are Facebook, Google, and Leetcode. In example 2, we have our input array words 1 to be the same words, and in this case, our words 2 is going to be L and E. And applying the similar logic as the first example, the only three words in this input array of words 1 that actually are universal, meaning L and E, are both subsets of those words, are going to be Apple, Google, and Leetcode, because all three of these words contain at least both an L and an E, right? Which is very important to know. And one more thing here. Notice how we don't actually need to have exactly only one E. We can have more than one E, as we see in Leetcode. As long as we have at least this many E's, well then we know that E is going to be a subset of the string Leetcode. So for the constraints here, we see that the length of our input array words 1 and words 2 of strings are never going to exceed 10 to the 4th power, which is relatively pretty big in runtime and memory time complexity. And for every single string length in both of these inputs, they're not going to exceed 10. And we're also guaranteed that all of the strings of word 1 are indeed unique, and words 1 and words 2 at any index I is going to consist only of lowercase English letters, really just meaning that they're always going to be valid inputs. So with the problem statement, examples, and constraints out of the way, I will give you guys a few seconds to just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what are some key observations that we can really make to this problem to really help us lead to our most efficient solution? Well, one way to really think about this problem is that really instead of comparing every word in words 1 with every single word in words 2, which would really be n times m, where n and m are the lengths of those two inputs, really, we can simply just combine the requirements of all of the words in words 2 into basically a single super word that we have to check that's basically going to be a representative for all of those words in words 2. And that's going to save us a ton of computation, making our solution also a lot more efficient, right? And for another very important observation to make in this problem, this super word that we're kind of going to construct, or rather the super word I should say, basically it can really just be represented as a frequency count of all the characters in word 2, right? So for example, if word 2 was the string E and the string OO, then the super word's frequency count would basically require at least one E and two O's, right? And really, that's going to really help reduce the problem into really just comparing character frequencies, right? So for example, in words in example 2, when words 2 is equal to L and E, really our super word would be 1L and 1E. That would basically be the representative of the frequency count of all the characters combined into one result that we're going to be checking in or rather from our words 2, which is going to really help us save a lot of computation instead of literally manually checking every single word or rather pair of elements from words 1 and words 2 using nested loops. Right? So basically, for a quick kind of like high-level rundown of how our solution is actually going to be structured, basically we're going to first build a frequency counter for the super word. That's going to be by taking the maximum frequency of each unique character across all the words and our words 2 input array. And basically for every single word in the words 1 input, basically we're simply going to check if it actually satisfies the character's frequencies in that super word. So if it has at least that much of a frequency for that specific word. And effectively, we're simply going to return the words in words 1 that meet the criteria by appending the valid words or universal words to a return list, right? So with that kind of high-level rundown out of the way, let's go ahead and dive straight into the code here. So what I'm first going to do is actually kind of initialize that counter that we're actually going to build for the combined max frequencies like we talked about before, kind of like the representative of the super word here. Basically, I'm going to call it B max, where they also refer to B as basically every single string in words 2, right? And this is actually going to be initialized to an empty counter, okay? And for every single B is going to be basically a regular string in our words 2 array to actually iterate over our words 2 array to help build our B max. Basically, what we're going to do is in each iteration, we're going to get the B frequency to basically be the counter at B, right? That's literally going to be the frequency of the current word or iterator B, which is going to be a counter at that B, its frequency correspondingly. And for every single character in this B frequency, right, that we initialize on line 5, basically we're going to set the B max to be the maximum of course, itself. So B max at the current character char, right, where chars are iterator are going through every single iteration in B freak, and B freak at char. Well, freak really just stands for frequency as the counter that we initialize on line 5. Okay, well, what does this really mean here? Why are we really doing all of this kind of big chunk of code? Basically, what we're doing here on line 3, bmax is equal to counter, we're really just initializing this empty counter. It's going to be an empty counter object that's going to be bmax, right? And really what this is going to do is it's simply going to store the maximum frequency of every single character across all of the words in words 2. Right? And then we start iterating through every single word, as we say B, where B is a single word, in our input array words 2. And on line 5, for every iteration of this for loop here, for each word B, we're basically creating a frequency counter that we call B frequency or B freq, right? And it's going to tell us how many times each character actually appears in this current word B, right? In this iteration of B. And effectively, as we're actually looping through every single character in the B frequency, which is the counter at that B, right? Basically, we're actually going to, for every single character in the B freq, we're comparing its frequency with the corresponding value in B max, right? And of course, if the frequency in B freq is greater, well then of course we have to actually update B max. And that always makes sure that B max is always going to contain the highest frequency required for every single character in the current word B, right? And again, what we're doing here, we're basically just really creating a frequency counter that we call B freq. It's going to tell us how many times each character actually appears in B from the counter of course, the current word B. Okay, so now that we've actually built up our B max hash map, I should say, or counter, I should say, sorry about that. Now let's actually initialize our result. Right, this is effectively what we're going to be returning. It's going to store all of the universal strings from words 1 that basically every single string or word in words 2 is a subset of. Okay, so once I initialize or basically declare my result, now let's actually loop through all the strings that we're going to call A as our iterator in words 1. So for every single A, like they say in the problem here, a string A from words 1 to be universal, to actually iterate over all the strings in our input array words 1. So in words 1, simply iterating over it, we then want to have a similar approach of getting the A frequency to be the counter at the current word A, right? Very similar logic here. And if all of these conditions hold to be true, so the first condition is, well, does A frequency at the current character, so I'm just going to call it char, does it at the current character, is it actually greater than or equal to B max at the character, because of course we want to have at least that many characters for it to be actual universal, for it to actually be universal for every single character in B max. I believe this is called list comprehension, or I guess in this case dictionary comprehension, however you would like to really comprehend it, or however you would really like to interpret it, right? But basically, if all of this is true, A frequency at the current character is greater than or equal to B max at the current character for every single character in B max. It's basically really just a really heavily dense or condensed for loop here that I don't know if it's more readable or less readable. I guess it really just works at the end of the day. It really has a similar meaning here. Okay. So let's go ahead and really iterate again, go back to what this code really does here from lines 8 to 11. Basically, after initializing this result, that's going to store the universal words. Then we're going to iterate through every single word that we call A as our iterator in words 1, right? And in this case, of course, A is going to be or represent a single word, okay? And for every single iteration or every single word A in the word 1 input, we're going to get the A frequency to basically be a frequency counter to track how many times each character actually appears in A, which we can really literally just get from the counter at that current index or word A, right? Now, what we're really checking here, if all of these conditions hold true, basically we're checking if A meets if A actually meets all the frequency requirements in this B max hash map. Right? And again, this all function is really just going to make sure that for every single character in B max, its count in A frequency is greater than or equal to the count in B max, right? So basically, if we go back to the example here, let's just take Leetcode, for example. If this is the current word A, and we have these two strings, E and O, we want the frequency of E in Leetcode to be greater than or equal to the frequency of E here in the string B, and we want the frequency of O in Leetcode to be at least the frequency of O in this string B, which is simply going to be 1. In this case, O and E both appear at least or more than 1 times, so this would actually be a universal word because these two would be considered hence subsets of Leetcode, right? That's really what this all function or conditional is really checking here on line 11. We want to at least have that many characters in this potential universal word string A from all the characters' frequencies in the string B or subset B, and if that's the case, well then great. If all of this is true, that means it is actually a universal word, and the A actually does meet the criteria of having a frequency of at least that many characters of B for every single character that's unique in our input string B, and so then we can append or add to our result, to that resulting list, the current word A. right? That really just means that it's going to be a universal word. And effectively, once this for loop is then executing, we simply have to return that resulting list because it eventually would have stored, once the for loop terminates, all of the universal strings in word 1. That basically every single word in word 2 is a subset of. So unless I made any syntax errors here, this should be accepted and it should be a valid solution. Okay, looks like I made a quick error here. So Bmax, oops, so I forgot to actually include the character, because we have to actually set Bmax at the current character char to be the maximum of these following indices, right? So now this should work. Sorry about that, guys. And as you can see, this is really just about as efficient as you can get. It really is just the most efficient solution. So to kind of reiterate what my quick error was there, basically on line 7, I forgot to actually set the index of char in this Bmax counter, basically hash map, if you will. Basically what we were really doing here, to kind of reiterate, basically for every single character in the B frequency, which we initialize on line 5, basically we're comparing its frequency with the corresponding value in Bmax. But if the frequency in B frequency was greater, well then we have to actually update the Bmax for the kind of final hash map with all the maximum frequencies of every single unique character in the string B, and then that basically makes sure that Bmax is always going to contain, again, the highest frequency required for a string A to be universal for every single character in the current string B, right? So for the time complexity of this solution, this is actually going to be a big O of n times L1 plus m times L2, and before I get into that, I kind of want to just kind of gloss over the code as a whole, kind of just reiterate how the code actually works as a whole. Basically, again, we're finding all of the words in words 1 that satisfy the frequency requirement of the super word that we built from words 2 with the maximum frequency hash maps, right? And basically, by actually reducing words 2 into a single frequency counter using this Bmax hash map here, really, we're simplifying this problem significantly, and we're really avoiding a lot of extra redundant computations as such, right? And this problem is actually a really great example of optimizing a problem using some pretty key observations here and data structures like this counter hash map, which is very important for that actual kind of super word simulation of our input array words 2, right? So again, for the time complexity, let me actually comment this out because it would actually be pretty advanced. Run time complexity. This is actually going to be a big O of n times L1, actually I think I should capitalize L just in case, plus m times L2, right? And to kind of define these variables here in this big O notation, basically n is going to be the length of words 1, L1 is going to be the average length of words in words 1, m is going to be the length of words 2, and L2 would hence be the average length of words in words 2. And why is that? Well, because really we're processing every single word in both lists exactly once to actually help compute the frequencies and determine the max frequencies of every single string B in words 2 and all the universal strings in words 1. And for the memory or space complexity, this is actually going to be pretty simplified. It's not too complex, but I'm still going to comment it out either way. So memory / space complexity, and I think I should capitalize the C here for readability here and formality. It's going to be a big O of U plus W, right? And the reason why this is because, of course, again, U is going to be the size of this Bmax counter or this Bmax dictionary hash map, and then W is going to be the size of the largest word in words 1 during the frequency check, because again, we're using those extra data structures or that auxiliary memory to actually build and store our solutions to this problem. And so this is actually going to scale pretty proportionally with our input size for the space complexity. Hence the reason why it's big O of U plus W. Right? Again, W is the size of the largest word in words 1 during this actual maximum frequency check and the universal words check. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.